Greetings and welcome to Calculus Part B. Our first live lesson will be on Friday, but I know some of you are anxious to get started, so I wanted to give you a few homework hints for Module 1. So Module 1 deals with optimization problems. So essentially what you are trying to do is identify maximum volume, maximum area, you're trying to minimize cost, maximize profit, and so forth. So optimization problems really help you to see what you can do with all of this calculus that you have been learning. So before we dive into that, I just wanted to quickly review your first and second derivative test and some of the steps that you can take to solve these optimization problems. So step one, I like to, if a picture is not provided, I always like to start with a picture or a diagram. I'm a visual and it just really helps me to lay things out. So step one is create a visual. Step two, identify variables. Step three, create an equation or use a formula. Step four, think about any potential domain restrictions. So if you're dealing with, say, area or volume, you know your values aren't necessarily going to go into, or the useful values won't go into the negatives. So you always have to think about possible domain restrictions. And then that last step is to identify the local max or local min. And remember, we have ways to identify these using calculus. You can always double check your work with Desmos and look for local mins and maxes. But remember, utilizing calculus, we use something called the first derivative test and the second derivative test. So we set our first derivative equal to 0. So first derivative equal to 0 and solve for whatever variable you're working with. So we're just going to be general, we're going to say solve for x. This gives you your critical points. Remember, your critical points are where you're going to find your local mins or maxes or points of inflection. So mins or max. To identify whether or not your critical point is a min or a max, we can use the second derivative test. So we take the second derivative, plug in our critical point. If it is greater than 0, then we have found a minimum. If it is less than 0, we have found a maximum. So that's just a quick review of the first and second derivative test. So what I wanted to do is just talk about some of the homework problems and give you some ideas for how to approach them. So for the first question, you're given a formula for volume, and it's asking you basically to maximize the volume. It gives you a little bit of information that really wasn't necessary, and I know that's thrown a few of you. It says the length, the width, and the height of the box must be less than or equal to 62 inches. Assuming the height is fixed, show that the maximum volume is, and then they give us our formula for that, and then it's asking what height allows you to have the largest volume. So again, you're just looking for your local max. So you would take that function that was given, derive it, set it equal to 0, and identify your critical points, and then take your second derivative and identify whether or not it is a min or a max. You could also graph it on Desmos and check your answer that way as well. Okay. For question 5 and 6, this was another one that stumped a few people. It says find two positive integers such that their sum is 10 and the sum of their squares is a minimum. Try not to overthink this one. I know it feels like we're in calculus, we have to overthink it, but not always. So think about two integers where the sum is 10. The sum is 10. So let's just say, how about 1 and 9? That gives us 10. 2 and 8. 3 and 7. 4 and 6. And you can keep going. I think there's about eight possible combinations. So you are looking for the two numbers where the sum is 10 and the sum of their square is a minimum. So let's check it out. If we square 9, we get 81 plus 1, that's 82. That's the sum of their squares. Sum of the squares here, 64 plus 4, so 68. We keep doing this until we find the lowest sum of their squares. So the lowest value in this right-hand column. Okay. The probably one of the trickiest ones on here is this problem. I believe it's 13. So it says if you can run at a speed of 6 miles per hour and swim at a speed of 3 and are located on the shore 4 miles east of an island that is 1 mile north of the shoreline. How many of you have just stopped reading and want to run away at this point? Sorry. How far should you run west to minimize the time needed to reach the island? Okay. So this problem is not as scary as it looks, but it can certainly be a little bit intimidating. I think the tricky part is the diagram, so I'm going to help you out with that. So here you are. And the problem tells us that you are 4 miles east of the island. So 4 miles east, and the island's 1 mile north of the shoreline. So here we go. So if this, we're going to call that x. And this would be 4 minus x because you're 4 miles east. This we're going to call y. Or sorry, we're going to call 1. And this we're going to call y. So we'll deal with the rates in a second. Let's first think about what type of equation we could use to work through this. So remember, step 1 was diagram and then variables. One of the steps that I didn't mention is if you have more than one variable that you're working with, it's best to get these all in terms of just the one. So let's look at this and think about, okay, well, what can I do to express y in terms of x? Because the question is asking, what is the best approach to get to the island? So basically you're going to run this direction and then swim this direction. So you're really adding your x. Yeah. You're just adding that, whatever that value of x is, plus this value of y. And you're looking to get there as quickly as you can, because you want to minimize time. So we have a right triangle. So hopefully that is screaming Pythagorean theorem, please use me. So we can solve for y using the Pythagorean theorem. So y is equal to the square root of 1 squared plus 4 minus x squared. So that's giving us this piece right here in terms of y. So remember, the distance you're traveling is x plus y, so the distance we're traveling, and I know you're thinking, don't do the whole problem for me. Don't worry. I am saving plenty of it for you. So that helps us to really see, okay, this is This is the distance that I'm traveling. The question isn't asking you about distance, it's asking you about time, and it gives you a rate. So there's another formula that hopefully is going off in your head. Distance equals rate times time. So if you have distance equals rate times time, that's essentially what you're solving for. Time is equal to distance divided by rate. Well, we have this distance here where he's running, and this distance here where he's swimming. So the rate at which he runs would go here, and the rate at which he swims would go here. All right, I'm going to leave it to you to take it from there, but that should help with the setup and help you visualize how to approach this problem.